Welcome to another mathematical moment from the American Mathematical Society. I'm Layla Sloman, and today I'm talking with Dr. Abiy Tasissa, a mathematician at Tufts University. Today we'll be talking about a new paper Dr. Tasissa was involved in, which used math to study the shape of jets created by colliding particles. Welcome, Dr. Tasissa, and thank you for talking with the AMS. First of all, in this case, a jet does not mean a kind of airplane, which may be what viewers are thinking of. So maybe you can start by telling us a bit about what kind of jet you're studying in this case.
So a jet is a set of particles which are typically produced as a result of experiments in collider physics. So this set of particles, we refer to them as jets.
What is useful about knowing the shape of a jet?
In understanding the underlying physics that happens in collider physics, and also to probe what's called the standard model of physics, jets give us some glimpse into the underlying phenomena.
So how does mathematics come into it?
An important thing is if you have two jets, or as we call them in this paper, two shapes of a jets, how do we compare them? How do we compare these events that happen in the collider experiments? And in a previous work, there was a notion of distance, just like we have distance between two locations. What's the notion of distance to be able to compare these two shapes or these two events? So the point of this paper was to further argue that there is a very natural distance one can define on the space of these collider experiments to be able to compare these two shapes.
So to those of us who aren't mathematicians, maybe it seems like a distance is a distance. So could you talk about what it means to have different ideas of distance and what that kind of looks like in this particular case?
Typically, when we think of distance, we think of what's known as the Euclidean distance between 2 points, right? So if I give you two cities or two locations, the distance that we get from the GPS will be the Euclidean distance. In many problems, for example, in physics or data science, what we have are not really locations or cities, but rather a different set of objects. For example, in the setting of this problem that we study, the underlying objects are distributions. So one way to think about this is imagine that we have two piles of dirt, and we wanted to ask, what's the distance between these two piles of dirt? So one natural notion is to just say the exact distance that we are all familiar with, which is the distance between these two piles of dirt. Another notion of distance is how much work does it take me to be able to transfer one dirt into another as much as possible by preserving the distance, or how much dirt I have to move. So this type of distance is called the Earth-mover's distance. So the notion of distance will depend on the application. It basically tries to capture what the similarity that I want to attain is should be captured in the distance. So while the Euclidean distance is extremely useful in a lot of applications, in this particular context, the objects that we are working on are actually distributions, and a very natural distance is this Earth-mover's distance, which tells us how much energy or work will require to transform one into another, and the minimum cost gives rise to this notion of distance.
Right. Yeah, that's a great visual, having the two piles of dirt. When it comes to colliding particles, what kind of image of an event are you thinking of? That how similar is it really to a pile of dirt?
A good question. So when we have these jets, when these collider physics experiments happen, typically, we have things called observables, which are things that we measure in the experiment, or things that we focus on, and these observables are typically energy flows or energy distributions. So it's not a particular value that we get, but we have a distribution. And the question is now, if I have two collider events, let's call them A1 and A2, given these two collider events, do I have a notion of distance between these two collider events using the fact that these are now two different shapes?
What type of mathematics ends up being used in studying these kind of problems?
One kind of mathematics that's used in this type of problems is what's known as optimal transport. So optimal transport is basically the definition that I gave earlier. If I have two distributions, how could I define the notion of distance? And in mathematics, a distance has to satisfy certain properties, and we have to make sure that this is a well-defined notion of distance. So for that reason, one area of mathematics that comes a lot in this is optimal transport. The other part of it is optimization. At the end of the day, when we have, to compute this distance, we have to solve a minimization problem. And to solve that, we have to employ optimization algorithms that are efficient, given that in a typical collider experiment, we want to make sure that our algorithms are scalable. So there's the optimal transport side, which gives us the theoretical grounding to be able to give a well-defined similarity. And there is the aspect of optimization algorithms to design fast ways to actually compute these distances.
So for this paper, what do you think the main takeaway should be?
Yeah, the main takeaway of this paper is the idea that if you have these things that happen in the collider events, and we have these things called jets, to understand or compare these jets, there is this natural metric, called the Earth-Movers distance, or we call it the Wasserstein metric in the paper. To be able to, compare, we show that it's a natural and faithful metric to be able to understand this phenomena. So it's basically giving a link. It's giving a link between the connection between the physics side of what happens and the geometry, the fact that this geometrical distance captures important information about the physics.
Right. So studying these jets of colliding particles, that's a pretty specific application. I'm wondering if you think that these type of mathematical techniques that you've used in this paper would end up being useful for other types of applications.
Yes, I think in this particular application, given the nature of the work and the interest of my collaborators who are physicists, we focused on the jet problem, but potentially this problem of comparing distributions using optimal transport could find application in many settings. The notion of using distance to compare, to classify, or to categorize shapes or distributions can find applications in image processing, in natural language processing and other areas.
What has it been like for you studying this, maybe sounds like new to you type of a problem?
Yeah, it's not within, it's not really the typical application that I work on. So it was kind of interesting for me to see how mathematics can be applied to study these fundamental problems, answering fundamental questions in physics, and not only at the level of formulating new ideas, which is in this particular case a notion of distance, but also how the importance of designing fast optimization algorithms to be able to actually compute these distances. So the fact that the mathematics allows us to capture important structure, and in addition, the role of optimization to be able to actually compute these distances was interesting for me to see it in the context of this application.